So you might remember a few years ago, they opened up an LA Fitness here in Royal Oak, right at the end of Washington here. And when they opened up, they had a couple decent specials. You could join for $350 and then pay $45 per month. Or if you wanted to join for a smaller fee, say $250, then your cost was $55 a month. So the question is, well, which one should I join? Which one of these, Sam, should I join up on? You do the top one? Okay, top one. Okay. All right. So this one, the 355 plus 45. I guess it depends on how long you're going to be there. Because if you're only there for a few months, then you're going to end up paying more. If you're going to be there for the long term, then yeah, this is the one to go. So the question is, how long do you have to be there before you break even? Well, turns out it's 10 months. 10 months is the break-even point for this little example. But the point of that is not necessarily to promote LA Fitness or anything like that. The point is the point of intersection is quite often of interest. That's what we're going to be looking for in this section. So there's a couple different ways to find that point of intersection. One of them is by graphing, like we just did. Another is by substitution, and another is by the addition method. Now, when you're trying to solve these systems of equations, there's more than just one thing that can happen. You can get 2 points, or excuse me, 2 lines that cross each other. That would be a solution. When you have a solution, your system of equations is called consistent. But that's not the only thing that can happen. Sometimes your 2 lines won't cross each other. Now, if they don't cross each other, there's no solution. Your solution is where your 2 lines cross each other. If you're not consistent, what are you? Inconsistent. Inconsistent. Yes, there we go. Now, the one last thing that can happen is you can actually have 2 lines that are essentially right on top of each other. So, for instance, you could have x plus y equals 2 as one equation. And when you graph that, you find x and y intercepts at 2, 0, and 0, 2 respectively. You could also have another equation, say 3x plus 3y equals 6. But guess what? It's going to have the same graph. So essentially you'll have 2 lines, one here, and then one right on top of it. So this is a different thing that can happen, a different configuration in working with systems of equations in the 2x2 case. If you have something like this, that's called a dependent system. And I'm hoping this is a review from the previous math class. So we will go over this a little bit quickly, but I did want to give you a reasonable review of this stuff before we move on into the new stuff, the 3x3 systems of equations of section 12.2. So let's remind ourselves a few things about 2x2 systems of equations. And I'll call them 2x2 because they're going to have 2 equations and 2 unknowns. We'll start with problem number 16. trying to find some decent scrap paper here. Okay, here we go. So problem 16 looks like this. We've got the equation, thank you, 4x plus 3y equals -1. 4x minus 3y equals -5. And we want to decide if the point -3/4 and 2/3 is a solution. So does that point satisfy this system of equations? Now if it does, then that would be the solution to our system of equations. So let's see how we're doing on this one. Well, keep in mind that this is an ordered pair. So that's your x and that's your y. Let's plug it into both equations and see if it works. So 4 times -3/4 plus 3 times 2/3. Does that equal -1? Well, it's a good question. Let's find out. There's going to be a little cancellation here. So I'll end up with -3 plus what? Plus 2. Good. There's some more cancellation here. So plus 2. Yeah, and that works. -3 plus 2 does equal -1. Okay. Let's take a look at the other one then. It has to solve both of these. Maybe I should say satisfy both of these. So 4 times -3/4 again. -3 times 2/3. We should get some more nice cancellation. We do. The 4's cancel. Leave me with -3. The 3's cancel. What am I left with when I cancel the 3's? -2. And that's equal to -5. Okay, so it works. That means this is a solution. That means a little bit more to our system of equations as well. It means it's a consistent system because we found a solution. There's at least one. And that's all you need to have a consistent system of equations. So it's just consistent. I haven't talked about dependent or an independent yet. But a dependent system of equations is when the two equations are essentially the same. It was the last example on our previous page. We had one equation right on top of the other. Essentially, in a dependent system of equations, one of these is a multiple of the other. Is that the case here, or are these two separate lines? Two separate lines. So if you're not dependent, what are you? Independent. Let's take a look at that one graphically. If we look at this one graphically on my favorite website, Desmos, do you think I'm going to see those lines cross each other? Okay, I got to vote for yes. Someone else tell me where they're going to cross. Where are these two lines going to intersect each other? So here we go. 4x plus 3y equals -1. All right, before I type in the second line, where are these two lines going to cross each other? Yeah, that's exactly the coordinates we mentioned. All right, let's make this a little bit darker. There we go. So at -3/4 and 2/3. That doesn't look quite right. Did I type this in right? Oh, that's a -6. That's why. Make that a 5. Perfect. So you can see the decimal value for -3/4 and approximately 2/3. Spot on. So it's a independent, consistent system. Now there's a couple ways you can solve these types of equations other than just graphing. I think this problem in particular reveals the pitfalls of trying to do this with graphing. I mean, it's tough to try and estimate the coordinates of these points based on a graph. So other methods by which we can solve would include substitution. So let's take a quick look at a few substitution problems. So solve by substitution. We'll look at problem 36 first. So with problem 36, we've got y equals x plus 2 and x plus 2y equals 16. Now this one's pretty nice. It's kind of tailor-made for the substitution method. You've already got y by itself here. So let's take this expression for y and plug it into the other equation. So that would be x plus 2 times that expression equals 16. So x plus 2 times x plus 2 equals 16. Now there's a magical thing and a nice thing that happened here. This equation only depends on one variable. It only depends on x. It's a linear equation. We can solve linear equations. Let's distribute the two. X plus 2x plus 4 equals 16. Combine like terms. 3x plus 4 equals 16. 3x equals 12, so x equals 4. Yay. Now if x equals 4, what does y equal? 6. Good. Let's take a look back here. Remember, y equals x plus 2. So if x is 4, I get 4 plus 2 is 6. Overall, my solution is the point 4, 6. Maddie, is this system consistent or inconsistent? Good, it's consistent. All right, consistent. Dependent or independent? What do you think? Are these two lines the same? No. If they're not the same, then they're independent. So nice. You've got a consistent, independent system. That's generally what we want, because that means that the two lines are going to cross each other. And that place where they cross is your solution. Okay. Let's try a different one by substitution. That'd be problem number 54. So 4x plus 8y equals 15. And x equals 2 times 2 minus y. That's our system of equations. Again, this is more or less tailor-made for substitution because we've already got one of the variables by itself. You've got the x by itself on the right-hand side of the equation. So let me do this. Let's distribute that and call it 4 minus 2y is equal to x. But I want to take that expression for x and substitute it into the other equation. Make sure you don't substitute back into the same equation. That would lead you to quite the wrong conclusion. Let's carefully substitute that back into this equation. So it's going to be 4 times something plus 8y equals 15. Now that something is 4 minus 2y. Why don't you see if you can't solve that? See what you get. And while you're doing that, I'm going to graph it. What'd you get? 16 equals to 15? All right, Angela, can you help them out? They're making a mistake with their arithmetic someplace. You all got the same thing? Wow, a group mistake. I've never seen that. All right. Let's see. No, that's not the one I want. Where's the other one? X equals 2 times 2 minus y. There we go. All right, so when you're trying to solve a system of equations, you're looking for where the two lines cross each other. Yeah, there's no place where these two lines cross each other because they're parallel. Now, without graphing that, you probably wouldn't see that. So what do you see? Well, let's check it out. When I distribute here, I get 16 minus 8y plus 8y equals 15. And of course, these like terms cancel each other out, and I get 16 equals 15. Well, that's not true. So what's happening is that there's no solution. Now we've got a nice way to say no solution in this chapter. What is our nice way to say no solution in this chapter? Inconsistent. Good, it's inconsistent. How about, yeah. Yes, exactly right. Nice one. If it was 15 equals 15, then these two lines would be really one on top of the other. In fact, I can show you that in just a second. Let's see. It's inconsistent, dependent or independent? Independent. The two lines are separate lines. Julian, yes, a great question. Let's see. If this number in here was 3 3/4, so that when I multiplied them together, I got 15, then it would be one line on top of the other. Let's see that real quick here. Let me change the equation here for the second line. Let's see here. Is that it? Let's see. I have to think a little bit. 3 3/4. All right, so this is really 4 minus 2y. All right, so if I made this 3.75, yeah, now you can see that the two lines are essentially the same. So they're one right on top of the other. And had that number been a little bit different there, this one been a 3.75, then they'd be two of the same lines. So you'd get 15 equals 15, and that means you have a dependent, consistent system. Very good question. Anything else on 54 here? Now this is one way you can solve a system of equations, is with substitution. But sometimes substitution isn't very practical. Sometimes it becomes kind of a pain to solve and do these things by substitutions. Let's take a look at problem number 40. Is this stuff looking pretty familiar? I mean, most of you, I think, had Math 1100, and I know that we did this. Yeah. It's a favorite, all right? Well, I guess what I like about it, and tell me if you at least appreciate it, is that It's a very practical application. I mean, I literally solved that myself when I decided what membership I wanted. I'm like, well, what makes sense? So I solved it. So, I mean, I always get that question, well, where are we going to use this stuff? Well, there's a nice place. All right. Well, let's keep going. Problem number 40. We're going to start working on the addition method. All right, but the hamster example, or the guinea pig example, that was new. That was new. All right. So 2x minus y equals, 2x minus y equals negative 21. And 4x plus 5y equals 7. What made this substitution method work for us is we were able to get rid of one of the equations, or excuse me, get rid of one of the variables and solve an equation that just depended on one variable. There's another way you can kind of get rid of a variable, and that would be to multiply one equation by something and add it to another. Now I'll do this two different ways. But suppose I multiply the top equation by negative 2. We'll see what happens if I do that. I get negative 4x plus 2y equals 42. And I'm going to add that to my bottom equation, 4x plus 5y equals 7. Does anyone see something nice that's going to happen when I add those two equations together? Yeah. The x's go bye-bye, right? They cancel each other out. And what are you left with? 7y equals 49, so y equals 7. Yay. That's half of your solution. I say half of your solution. What do I mean by that? Yeah. Typically what I would do at this point is plug the y value back in here and solve for x. That's what you should do. But just for the extra practice, let's look at this problem a different way. Suppose instead of eliminating the x's, I chose to eliminate the y's. Can somebody see something I can multiply the top equation by to eliminate the y's? 5, right? So if I multiply by 5 on the top equation, then I get 10x minus 5y equals negative 105. 4x plus 5y equals 7. And when I add these together, I get 14x equals negative 98. And it looks like x equals 7 again. And x equals negative 7. There we go. Okay, so here's a quick important little note here. How could I tell that I got these things right? There's two different answers that I'd take here. Other than, well, redo the problem. All right? How could you just tell, with a lot less work than we did, that I got the answers right there? Into where? Yeah. Plug these into these two equations. Now, is it enough that they satisfy one, or do they have to satisfy both? They have to satisfy both. Let me be very clear about this, folks. This is a cool section because you can check your answers before you hand in an exam paper on this stuff. All you have to do is plug them in there and test them. So I would encourage that you do that. Let's take a look at problem number 54. You're right, we did. How about, my bad, 24. Five x plus 2y equals 6. 40x, is that right? 40x? 40x minus 4y. That's negative 10x. Okay, my bad. I didn't All right, that makes more sense. Negative 10x minus 4y equals negative 12. Again, let's solve this by the addition method. Suppose you're going to eliminate the x's. What would you multiply by the first equation by to eliminate the x's in the second equation? Just positive 2, right? So multiply the top equation here by 2. What do I get? (10x plus 4y equals 12) added to negative 10x minus 4y equals negative 12. What do I get on the left-hand side? 0 equals 0. Wow, 0 equals 0. Well, that's cool. All right, 0 equals 0. But what's that telling us about our system of equations? Nice, who got that? Well done. They're dependent. What's happening is that one lands right on top of the other. They're a dependent system of equations. So, wow, cool. If you were to graph these, you would see one line, one on top of the other is really what you're going to get. But it's a dependent system of equations. Okay, one last reminder type problem from this section. Are we okay with the examples we've got to so far? Anything on this? Okay. That last example problem is number 30. (3/5 x plus 1/4 y equals negative 11/10. And at the same time, we're also going to work with 1/8 x equals 13/24 plus 1/3 y. Okay, I know what you're thinking. God, how exciting we could do a problem with fractions. Woohoo! Just chills setting up and down your spine. Yeah, fist pump, yeah. All right. Well, in as much as most of you, I might even go so far as to say all of you, probably really don't like working with fractions, let's get rid of the fractions. What could I do to get rid of the fractions for the first equation in number 30? The 20, what's that 20 called? The L, yeah, CD, least common denominator. So the least common denominator is 20. So each one of these things has to get multiplied by 20. So 20 times 3/5 x plus 20 times 1/4 y equals 20 times negative 11/10. Now, as I do that, there's lots of nice simplification. I think I've mentioned this mathematical operation before. Gazinta. Remember that one? 5 gazinta 20, 4 times. 4 times 3 is 12, so I get 12x. How about the next term? Plus 5y equals minus 22. Test yourself on the next equation. What's the LCD there? (24). So 24 is our LCD. Every one of these terms gets multiplied by 24. So 24 times 1/8 x equals 24 times 13/24 plus 24 times 1/3 y. See if you can't simplify that. How's that going to simplify?
It's going to be 3x equals 13 plus 8y.
Perfect. 3x equals 13 plus 8y. Are we okay with this first step here? Let's keep going then. So let me write those two equations together. I've got 2x plus 5y equals negative 22. And then 3x equals 13 minus 8y, or plus 8y. Now you're free to solve these any way you want, unless you've got some easy expression to work with. I would typically suggest the addition method. And before I do that, what I'm going to do is I'm going to move the 8y to the other side. So I'm going to leave the 13 on the right-hand side. When that 8y moves over to the left, what else happens to it? Changes signs. Good, so changes size, changes signs. All right, I'm getting closer. If I'm going to solve this by the addition method, can anyone see an easy way to multiply one equation or the other by something so that I can get some cancellation? So let's multiply. If you notice, 3 goes into 12 evenly 4 times. We can multiply this by negative 4. What's that going to give me? Well, the top equation is going to stay the same. The bottom equation goes negative 12x plus 32y equals, oh boy, that'd be negative 52. When I add these together, I get 37y equals negative 74. Close. Y is equal to negative 2. Now, do I want to go back and eliminate the y's to solve for x, or is there an easier way I can do this? Yeah, I just take this, which is half of your solution, and plug it in one of the equations to get the other half. So you can plug it into here, here, here. Let's go with that first one, or that second one there, because at least I've got the x on one side. So it would look like this. 3 times negative 2 equals 13 plus 8y. So I get negative 6 equals 13 plus 8y. Oops, I screwed that up, didn't I? I substituted in for the x. I should have been substituting in for the y. My bad. 3x equals 13 plus 8 times negative 2. 3x equals 13 minus 16. What does x equal? Negative 1. When you look up your solution in the back of the book, they're going to write it in the form of an ordered pair. So your x and then your y. For myself, on an exam, it's enough if you just circle your answers at the end. That's fine.